it was larger than 0, but it was also smaller than 1, okay? So there was no room for approximations, at least in the couple of examples that we covered. Now let's assume a case when the frequency, it is 10 gigahertz, and the relative permittivity is 12.9, okay? Let's assume the mu r is equal to 1. So what do we understand when we have mu r is equal to 1? We get that this is non-magnetic. This is something that we observe, or that's how we can interpret this one. And let's assume that it is given that the tangent of the lost angle is 5 times 10 to the power minus 4, okay? So this is what is given for us. Now the question is, let's try to identify the propagation constant and the eta. Find alpha, beta, and the intrinsic impedance, or impedance of the medium. So we're just given the tangent of the angle, but we are not given conductivity, and we are not given some other parameters. So what we can try, or actually if it's ever needed to find that, we can use these expressions that the tangent was equal to sigma divided by this number, and also this was this divided by this, okay? So these all three numbers, they are going to be, when I say three numbers, these three expressions, they are equivalent to each other. They numerically report the same value, 5 times 10 to the power minus 4. So if you want to find what is the conductivity, because it is not given initially, it's simply easy for you, because you can multiply this factor with the frequency and permittivity, and we can get the conductivity. So now in this case, we have alpha, which alpha in this case is going to be omega mu permittivity divided by 2 square root. You can correct me in here, 1 plus. There is this small factor, so this is going to be 5 times 10 to the power minus 4. This is square. This is 1 over 2 minus 1 okay, so this is what we are looking for in alpha. And then we notice that this 10 to the power minus 4, if we find the square, what is it going to be? It's 10 to the power minus 8. 1 plus 10 to the power minus 8 is almost 1. Okay? And, but wait a second. It's almost 1, but not exactly there, which means that this is going to be, we know, 1 plus x to the power n. This is equal to 1 plus nx, right? This is the approximation, which means that this approximation is also equal to 1 plus 1 over 2 times 5 squared times 10 to the power minus 8. 10 to the power minus 8, okay? And this 10 to the power minus 8, this, yes, and we do minus 1, so we subtract minus 1, and then in the final answer, so this is going to be some very small number. So we are going to get omega is 2 pi 10 times 10 to the power 9, so this is omega, times permeability. And again, we are left with square root of 12.9 divided by 2. We can divide also with 3 times 10 to the power 8, because you know that this permeability times permittivity, this is what what will come out. We have the square root of 2 here again, so we just wrote this term, and then from this term here, we took the square root of this one. It was, so this is going to be very, very small. So help me for a moment here. Is this the expression for alpha? Yes, we take the square of that, and the square of that is taken the square root. That's where we have this parameter. We subtract 1, and then we apply the square root again. Okay, so let me see. I think we can see this part of the board. So this is this term, 1 over 2, 5 squared, 10 to the power minus 4 squared. Okay, now 1 is gone. And this is all 1 over 2, right? We forgot this one. Let me check the expression. Yes, this is the case. And this will be equal to, so let's not forget, this was just the approximation to follow up with this expansion. So this is to the power 1 over 2, and then the expression, it comes out to, we can simplify a few terms. This is 3, we can keep this 2 pi, 10 to the power 10 times 10 to the power 9 divided by 10 to the power 8, we get 10 to the power 2. We can keep this. We can keep a 3 here, the square root of 2, so we are simplifying as much as possible. And then what is left, we have the square root of 12.9, it's still there, 12.9, times the square root of 1 over 2. Now let's write this one. This is 1 over square root of 2. Then 5 squared, square root, we get a 5. And 10 to the power minus 4 squared, square root is 10 to the power minus 4. Okay, so this is alpha. The value of alpha is the approximated one. It is going to be, so this is equal to, this 2, it can cancel out the square root of 2 and square root of 2. So we'll have here anyway, so this 3, we can keep things as elegant as possible. And let's not forget that this was still, we got this initial value, 5 times 10 to the power minus 4. And this is going to be, this 3 can cancel the pi. This is 3.14 divided by 3, it's gone, it's gone. Square root of 12 is almost 3, 4, 3 times 3, yes, it's almost 3. Probably it's better if you cancel, anyway. This is 3, this is 3. But let's assume for a moment, this goes like this, 300 times 5, we get 1500. 1500 divided by 10 to the power minus 4, we get something like 0.15, approximately. So the value of alpha, in this case, we said 0.15, we said, the exact value is 0.19, approximately. So this is going to be 0.19 NP per meter. Okay, so we found the alpha. Now that we have the alpha, we can also calculate beta. And beta is equal to, now this beta, we can apply the same expression, but we know that this is going to be, let's not forget, let me write here in red. So if this was beta, because beta and alpha, the only difference is that here we get a plus 1, okay? So if we have plus 1, the expression of beta is going to be much simpler, because here 1 plus 1, it will be 2. 2 plus something which is in the order of 10 to the power minus 4, it's still 2. So out of this old expression, we will be left with the same approximation we used in the previous hour. We get just this, mu this, okay? So beta, after substitute everything, we get the number of approximately, let me see, I don't have it, but let's try to calculate this again. 2 pi 10 to the power 10 divided by 3 times 10 to the power 8 times the square root of 12.9. Square root of 0.9. Can someone calculate this with a calculator? So
7.51 times 10 to the power 2.
say it again,
7.51
Yes.
times 10 to the power 2.
Okay, thanks. This is 7, yeah, okay. This is what we get. So this is radian per meter. And then, so let's write this one. The unit of this one is radian per meter. So let's not miss this. And then immediately we can calculate a few parameters, such as the velocity or propagation velocity. This UP, this is equal to omega divided by beta, okay? And we can also find the wavelength, which is going to be 2 pi over beta. But let's find the propagation here first. This is going to be equal to, again, 2 pi 10 to the power 10 divided by 7.5 by 10 to the power 2. Okay, let's have this expression like this. And 10 to the power 10 divided by 10 to the power 2, we get 10 to the power 8, which is the order of the speed of light. So this is 2 pi divided by 7.5, we get a number which is smaller than 1. So what is 6 divided by 7? 6 divided by 7, what is it? There's 0.8 something, 87. 0.8 is approximately. What is it?
0.84.
84, okay, that's better. 0.84 times 10 to the power 8 meter per second. Okay, if this was in vacuum, this would be something like 3 times 10 to the power 8. So it looks like we lost a lot of, like, we divided by, what is this? Didn't count at a pace, like 20%. It's like 20-25% of the speed of light in vacuum, meter per second. And this is C, okay? But in this medium, with these parameters, we come up with a very low conductivity, we get this term. So now, this was almost negligible conductivity. Now let's assume a case, not assume, but let's just go over for a moment for cases when we have perfect conductors. Perfect conductors, they are completely perfect lossing mediums. So if this is the case, then you know that in the expression for alpha and beta, we have this term. 1 plus is plus, right? Sigma over omega permittivity. This is all squared. This is square root minus 1 plus 1. For alpha and beta, okay? So alpha is the top one, beta is the bottom one. So when this is much larger than 1, these ones are gone, okay? So, but I think we have also this factor, right? I forgot this. What was this? Omega, I think it's this, divided by 2. Is this correct? Can you check if this is correct expression? So, alpha and beta, I expect them to be equal to this expression. Is this correct? Can you check it with what's on the board? Is this a correct expression? So now alpha and beta, if this is 1, with a very large number, this is going to be still this large number. So the square root is a square root. It will be the same number, minus 1. It will still affect nothing. So this alpha and beta, in principle, this will be equal to omega. I mind this term first. Permittivity divided by 2 times sigma. Wait a second. Square root, the number itself, and then it will have the square root of this. Yeah. So these two, they will be equal. So it looks like even alpha and beta for perfect conductors, they're going to be equal to each other. So, and then this is equal, so this permittivity cancels this term, and this omega, it will be square root omega permeability sigma divided by 2. I think this is omega permeability sigma. Okay, that's good. Okay, so we got this, and we see that this is equal to alpha and this is equal to beta. So that's what we get for alpha and beta. And now, since alpha and beta they are the same number, we also observe, we're going to see that the eta c, or the intrinsic impedance, which is a complex number, is going to be equal to mu omega divided by sigma. This is square root e to the power j times pi over 4. Okay. So this is what we get, which means that numerically the amplitude of the electric field with respect to the magnetic field intensity, it will be modified by this magnitude, and the phase, it will be modified by this much, which means that the magnetic field intensity will lag behind. So we can write it like this. So H vector, it lags behind E by this much. Okay, so this is what we have to report, or this is how we give the results. Now let's see if we can identify deviation constant. Okay, so here we have this connectivity, and we have also the phase. Let's assume that the propagation speed is equal to 720 meters per second at a frequency of equal to 3 megahertz. So here we have a specific frequency, we get this propagation speed. And the question is, let's see what different parameters are equal to. First of all, actually, probably we can even try to identify the propagation speed, which is equal to, so normally this value, this UP, this is equal to omega divided by beta, okay? And then the beta is equal to, so let's see what we get here. So this propagation speed is equal to 2 pi times the frequency. The frequency is 3 times 10 to the power 6 hertz divided by beta, and beta is given by, let's write the beta here. Beta, maybe it's best if we substitute this in here. So this is omega. We divide this by square root of omega, and we divide by square root of permeability, divide by square root of sigma, and the square root of 2, it comes up here, okay? So then this is going to be equal to, we get square root of the angular frequency, we can put a 2 here, okay, we can survive the 2, and we divide by square root of mu sigma, okay? Then these numbers, again, so we started the same expression, so let's substitute the values here, but this is, can you follow me here? So this, let's substitute the values for this specific expression here, and so here we have the square root of omega. The square root of omega is going to be this. So this is square root of omega times square root of 2, okay, which we got it there, square root of mu. This is a non-magnetic material because we are not told anything otherwise. This is going to be 4 pi times 10 to the power minus 7. This is the vacuum permeability times sigma, the conductivity, which is 5.8 times 10 to the power 7. Okay? So, if we check the numbers, we get here 2 pi times 2, they cancel the 4 pi, and then we get here 10 to the power minus 7, 10 to the power 7, they cancel out. We get here 3 divided by square by 5.6, this is almost 0.5, like almost 1 over square root 2, okay, times 10 to the power 3, times 10 to the power 3. So this is, I think this is exactly what we found here, okay. This was given actually, but we can even also derive it, because we know that 1 divided by square root of 2, 1 divided by 1.4 is like 0.7. 0.7 times 1,000, we get 720 meters per second. Okay? So apparently, in a material which is very conductive, with a very high conductivity, based on the values that we find here for alpha and beta, we conclude that the wave, it propagates relatively slow, or very slow. You see the speed of light? It's going at 700 meters per second. Okay? What is it? 1 kilometer per second. It's not that slow, well, compared to our vehicles at least. What else we can find here is that we can try to identify also what is the lambda. So by the way, did we find beta? No, we didn't. Okay. So if you didn't find beta, let's find it because we find it useful. So alpha is equal to, again, series of numbers, but actually this 2p.
Professor.
Yes. Yes.
Why are we finding the propagation speed when we already defined it as 720 meters per second?
Well, we are also checking our equations, okay? This
Okay, so now if we want to find beta, which propagation speed are we going to use? The one that we are given or the one that we calculated ourselves?
Well, most probably they are going to converge to the same value. Okay, you can use either one. Most probably that's going to be the same. Or for beta, we can, let's see. This is, but this is the approximation. So for beta, actually we can use this. But actually, why do I need the beta? We can use beta to find the wavelength. Okay. Because lambda is always equal to 2 pi over beta. But is it clear, this thing? You are right. This is given. Why do we find it again? It's like double checking our formulas, okay?
Okay, that's correct.
And let me think for a moment. Yes, we made use of the frequency, okay? Which means that this speed that we just found, this is going to be different if the frequency was doubled, okay? If it is 6 megahertz, what will be this is going to be 6, this will be multiplied by the square root of 2, so it's going to be this number multiplied by, so it's going to be 1000 actually, because the square root of 2 is square root of 2, so at 6 megahertz, we can write it here, at 6 megahertz, we have the speed is 1000 meter per second. Okay, here we get another number, which we can get from this expression. So if you continue again, beta is equal to 2 pi times 10 to the power 6 times 3 times 4 pi times 10 to the power minus 7. So we're writing this times 5.8 times 10 to the power 7. This is a huge conductivity. This is copper, superdioid, which we use it often in electronic circuits. We divide here by 2. This whole term is squared, so 2 is gone, and then we have here 10 to the power minus 7 with 10 to the power plus 7, and we get here, I mean, we can work around. Let me see if I have the numbers. Actually, I don't have a number here, but it's around, okay. I have something like 10 to the power 4 pi, approximately. 10 to the power 4 times pi. And let's check, because here we have pi square. Square root of pi square is pi. The pi will be left there. This is 10 to the power 6 times, so here we get 10 to the power 7, and 10 to the power, so 3 times 4 is 12 times 6. We get around, we get another, wait a second.
Professor, it's 6 Faraday Josh or deficit powder.
Josh or deficit powder. Okay.
Oh.
Thanks. That's perfect. Okay. So this is the beta, and let's not forget this is radian per second. Okay. But let's write this one equal also 2.6 times 10 to the power 4 NP per meter. Okay. Now, if you follow me, this is not exactly, let me write this equivalent. Okay. These are not equal. But I want to say that this is equal sign of alpha. Okay. Numerically, alpha and beta are the same, but beta is equal to this is equivalent to an alpha, which is this. A good follower of the class will not be confused if you see different units over there. Okay. Okay, that's good. So we found the alpha, and then the next possible question is, for example, to identify what happens. Wait a second. So we can find skin depth. The skin depth is going to be something like 1 over alpha, which is going to be equal to 1 over 2.6 times 10 to the power 4. And the skin depth, for sure, it looks like it's going to be something in the order of millimeters. And this skin depth, numerically, this is going to be 0.03 millimeters, or this is equal to 30 micrometers. Okay. So to see the distance where this wave is going to penetrate, you need a microscope. Okay. So the thickness of a hair, so if you pick up your hair, you put it under a microscope, the thickness of a hair is between 30 to 60 micrometer. So this is how deep this will go into this metal piece. So 3 megahertz, this will penetrate only a hair thick line of material. Of course, it's not this much, right? You are engineers now. You know that anything, if it attenuates, whatever the amplitude is initially, this is going to go like this. And we know that at one delta, so at one distance of 30, let me write it, maybe we write it 30 micrometers, okay? This will be decreased, the intensity, it will be decreased by how much? So we're going to have that A, 0, divided by A, this is equal to e to the power minus alpha times z. How do we get it? It's always, we know that A, the amplitude, is equal to A0 times e to the power minus alpha z. So we know that this alpha, this is the attenuation constant. So again, let's see if the expression is correct, because sometimes I do confuse these. So we have here if this is the amplitude modified by this, we get that A divided by A0, okay. This is wrong then. This would be the A later divided by A0. So we divide both sides of the equation with the initial amplitude, okay. You see these are cancelled out. This is going to be equal to e to the power minus alpha z. So this is equal to 1 over e to the power alpha z, okay, which is equal to e to the power. What is alpha? Alpha is 10 to the power 4. Okay, 10 to the power 4 times z. What was this specific length? This was 30 micrometer. Okay, so 30 micrometers. This will make this 30 times 10 to the power minus 6. I'm afraid minus 6. This is approximately. Wait a second. Yes. Anyway, this is 10 to the power 4, 10 to the power minus 2, 10 to the e 1 over e to the power. This is 30. 10 to the power minus 6 times 10 to the power minus 4 is 10 to the power minus 2, 10 to the power minus 1, 0.3. E to the power 0.3. Okay. E to the power 0.3. What is it? It's going to be 1 over to the power 2.7 to the power 0.3. Okay, so this is so when we say that the wave would penetrate 30 micrometer, it's not exactly true. We know that it will penetrate a little more, and theoretically it will go to infinity, but it's not possible. Anything which, because we know that things converge to a perfect zero only when z goes to infinity. Okay, so we know this the convergence of these functions. So we talk about, this was just the skin depth, and I think this is most that we can make from a conductive material. Okay, I think time is, we're very close to the end of the time. Do you have any question? Bjorna? Okay, I see Bjorna had a couple of comments, thank you. Okay, no injet by chart. Asiya?